Well, good afternoon. Figuring that I had 10 minutes, I figured I would focus on one example to tell you one specific aspect of our work on organic solar cells. Before I did that, I thought it was important for me to share with you some statistics. So I gathered this information. And so if you've seen this, bear with me for a couple moments here. So if you look at the global population stands at about 6.4 million people. And of those 6.4 million people, about 300 million reside in the United States. That makes it 5% of the global population. Now, if you ask the question of how much energy we consume, the global energy consumption stands at about 460 quadrillion BTUs. That's British thermal units. And quadrillion is 10 to the 15. Of those 460 quadrillion BTUs, about 100 quadrillion BTUs is being consumed in the United States. Okay? Those are all big numbers. So what do these big numbers mean? If you take these numbers, divide by the population, and then divide by the number of days there are in a year, and then divide by, let's say, the energy density of gasoline, what you get out is that the world consumes energy equivalent to 1.5 gallons of gasoline per person per day. And the United States then consume energy equivalent to 7.5 gallons of gasoline per person per day. So this is quite an alarmingly large number, considering that we probably don't even drink a gallon of water per person per day. Okay? And from this number, you'd gather that, yeah, I mean, there is an imminent need for us to find renewable energy that is A, sustainable, B, has negligible impact on the environment. And that's why we look towards the sun. So I'm showing you here the spectral irradiance of the sun. Okay, the solar radiance is at 1 kilowatt per meter squared. And if you take those units, what this means is the annual sunlight gives energy at about 3.6 million quadrillion BTUs. If you do that same kind of analysis, what this means is if we can effectively and efficiently harness solar energy for an hour, that's enough to power human activity across the globe for an entire year. Hence, this motivation and this drive for solar energy and solar research. So solar cells are used to convert sunlight to electrical energy. First-gen solar cells are these single crystalline type silicon devices. The thermodynamic efficiency, so this is the maximum achievable efficiency that these devices can hit, is about 33%. In the lab, they've been demonstrated to be between 20 to 25%. Now, if you incorporate them as modules and you put them on roofs, their efficiency drops a little bit, so it's about 18%. The biggest problem with these first-generation solar cells is the cost. Okay? They're way too expensive compared to coal. So there's this next generation or second generation solar cells. These are thin film devices, so they're polycrystalline. That drops the cost significantly, but here you take a hit in the efficiency as well. The materials that are used to make these thin film devices are cadmium, telluride, for example. They're rare earth metals. They could be toxic. And so we wanted to ask a different question. So I'm plotting here efficiency as a function of cost, reminding you that Gen 1 solar cells are right about here. Gen 2 solar cells are right here, so these are the thin film devices. Gen 3 devices we didn't talk about. These are the ones with fancier architecture, and so they're more expensive, but they're also more efficient. What the organic electronics community is asking is whether we can target right about there. We take a hit in efficiency, but we can dramatically lower cost. Indeed, market analysis that's been done has shown that if we can make about 10% efficient devices, we're in business. Okay? So that's the question we want to ask. Just quickly, let me show you how an organic solar cell is built and how it works. So here you typically start out with a glass or a plastic substrate. Okay? You have a transparent anode, and then you put down your organic layers. You need an organic electron donor, and you need an electron acceptor. And then you put on your cathode. So here are energy levels that are associated with the donor and the acceptor. So this is the LUMO level and the HOMO level, or the conduction band and the valence band. And so when you shine light, light gets absorbed in the donor, and then you generate an exciton. This is a tightly bound electron and hole pair. The electron then shifts to the LUMO level, and the hole remains in the HOMO level, and these get collected at the external electrodes. So solar cells are inherently not very efficient devices. Organic solar cells especially are not very efficient. The highest efficiency that's been reported a couple years ago is about 6%. Okay? And you can begin to understand why that is the case. the efficiency that's associated with a device is a compound of all these different efficiencies. So if you have one single step that's not efficient, that sort of propagates onwards. To characterize these devices, you plot the current density as a function of voltage, and you get a diode curve, and it's really the area here that's below the zero line that gives you how efficient your device is. The bigger the area, the better your devices are. Now, I'd like to call your attention back to how these devices are made. You'll notice that these devices are often built from the bottom up. Okay? You put down one layer, and then you put down the second layer, you put down the third layer. And that's because, we're following what's been established for the silicon industry. But organic is a completely different beast. They're frequently mechanically and chemically fragile. And so if you're using the same technologies to put down and pattern the cathode, for example, on the organic layers, you can potentially damage the organic layers. And so what we'd like to focus on is come up with non-invasive processing technologies to make these devices. So here in this example, I'm showing you how we can laminate to make organic devices. So the idea here is as follows. You want to make these devices separately, okay, the different components separately. And then in one final step, you bring them together. So in this example, we've basically patterned and deposited electrodes separate from the active layer. Here we're using polydimethylsiloxane. This is silicone. This has the same chemical structure as the RTV that you use to caulk your bathtub. You can pattern and deposit your electrodes without harming the photoactive layer. And then when you're ready, you laminate to make contact. Now, there are several merits associated with this lamination procedure. First of all, you have this modular construction of devices, so you can individually optimize the different layers. Second of all, you have custom engineering of the interfaces. So I've mentioned that charge extraction is a problem. You can imagine putting down chemical species here that can enhance charge extraction. And this is something that you can't easily do when you're building things from the bottom up. Finally, you can imagine doing this over large areas. And if you do this over a large area, it can potentially enhance fast throughput combinatorial testing of new materials. So we're working with a chemist right now who's going to synthesize a bunch of these new materials. And so we can inkjet print them down and laminate and test them really quickly combinatorially. So I wanted to show some data. So here are current density plotted against voltage for different contacts that we've made to the same photoactive layer. So we're putting down one contact, we're taking it off, we're putting down a second one, and then we're taking it off and we're putting down a third one. The point of this graph is to show you that this technique is actually really robust. It does not depend on the contact that you're making. What you're testing really is the characteristics of the photoactive layer. Now looking to the future, how scalable is this process? We believe this process is scalable, and it's compatible to roll-to-roll processing. So these are processing technologies that have been developed and established for the newspaper industry, for magazines, and whatnot. And if you take potato chip bags, for example, where they're depositing aluminum, and these are the specifications for depositing aluminum, if you use those specifications as a benchmark, you only really need about 100 machines to operate for a year to make 10% efficient solar cells. Now, of course, I'm not saying that organic solar is the way to go, but using the sun is clearly going to be one of the ways, and we think this is a good way to move forward. Oh. So just to show you that printing is possible, so these aren't solar cells, but these are sort of backplanes for displays that we've printed using sort of similar technologies.